So at this point, you're probably very familiar with the idea that electrons can occupy different energy levels while orbiting a nucleus. It turns out that as electrons move from one energy level to another, light can either be emitted or absorbed, and we use the Rydberg formula to calculate the energy of that light that's being emitted or absorbed. So let's start with the basics. So energy levels of electrons in an atom are what we call quantized. Quantized. So what does quantized mean? It basically means that these energy levels exist in discrete units, right? So fixed energy levels. So in other words, we see this atom right here. So we see we have three different energy levels. We call the center, the one closest to the center n equals 1, n equals 2, n equals 3, and so forth. Theoretically, there could be an infinite number of energy levels moving outward. And moving between energy levels from 1 to 2, 2 to 3, and vice versa requires either the absorption or the emission of some amount of energy. And that amount of energy needs to be in discrete units. It needs to correspond to the difference in energy between the orbits. So things you should memorize. So the first thing is light is emitted if an electron goes from high to low energy. So for example, going from n equals 3 to n equals 2, energy is emitted. So emission. Whereas the converse is true. In order to go from a low energy to a higher energy level, you need to absorb energy. So to go from n equals 1 to n equals 2 requires the absorption of some sort of energy. Because the way you can think of it is that the higher the energy level, the higher the energy. And so in order to go from low energy to high energy, you need to absorb some sort of energy from outside the atom. So this is something you should memorize. And then finally, light is quantized, as I mentioned. So only certain wavelengths of light, which match these differences in energy levels, can be either emitted or absorbed. So even the emitted and absorbed light is quantized. All right, so the formula we use to calculate the wavelengths of light emitted or absorbed is called the Rydberg formula. And the Rydberg formula has a lot of different variations. If you Google the Rydberg formula, you'll see a bunch of different formulas, and so it can be very confusing. It's best if you just stick with one version. And so I'm going to give you one version, and if you like this one, stick with it. If you like other ones, that's okay too, but just for the sake of consistency, use one formula and stick with it. So the Rydberg formula I'm going to use is delta E is equal to negative R times 1 over NF squared minus 1 over NI squared times z squared. Some formulas don't include the z squared term. Technically, this needs to be there because it doesn't only work for hydrogen atoms. It includes other atoms as well, like helium and lithium, etc. So what do all these mean? Well, delta E is your difference in energy levels between your final and initial. R is your Rydberg constant. Now notice here that Rydberg constant is equal to 2.178 times 10 to the negative 18 joules. The Rydberg formula can get confusing because there's many different forms. And so if you Google this, you might see a form where you use a different Rydberg constant, like 3.29 times 10 to the 15 seconds, or 1.097 times 10 to the 7 inverse meters. All of these can work and get the right answer. You just kind of have to use the equations a little bit differently. So let's in this video, I'm just going to show you this one equation, which will get you the right answer. You can also use different forms. That's okay too. But for the purpose of this equation, we're using the Rydberg constant that has units joules. And F is your final energy level, and I, excuse me, is your initial energy level, and then Z represents your atomic number. This is what you find on the periodic table, and it represents your number of protons, as we've seen before. All right. Okay, so let's use that equation to solve a problem. So the problem says, suppose that an electron in a hydrogen atom makes a transition from n equals 3 to n equals 5, so it's increasing energy levels, is light emitted or absorbed, and then calculate the wavelength of the corresponding light. So let's start with answering the first question, right? So if it's moving up, if it's moving to a higher energy level, is light going to be emitted or absorbed? Well, we saw this in the previous slide. Whenever you're going from low to high, so your n equals 3 up to n equals 5, excuse me, that will require the absorption of light. So light must be absorbed, and then they ask us to calculate the wavelength of the corresponding light. This is a clear example of a Rydberg equation. This is an example of a problem you can see on your midterm. The moment you see transition levels between n equals 3 to n equals anything else, that's a giveaway that it's going to be Rydberg. So I write the Rydberg formula. That's my first step. Delta E is equal to R times 1 over NF squared. Or, excuse me, it should be a negative here. Let me just make sure. Yeah, so there is a negative here. 1 over NF squared minus 1 over NI squared times E squared. Here we're dealing with a hydrogen atom, and the number of protons in hydrogen is just 1, and so this will cancel out just to 1. If it was a lithium or a helium, we would have to um, uh, plug in a 2 or a 3, etc. Okay, and then we just start plugging in. So we know that for delta E, we have, that's equal to Rydberg. So that's negative 2.178 times 10 to the negative 18 joules. 1 over NF, which is my final, that's going to be n equals 5. So that's 5 squared. Minus 1 over my initial, which is 3 squared. So that's going to be 9. And then z squared is just 1 squared. All right, and then we plug this into our calculator. We can solve for delta E. And we get a value of 1.55 times 10 to the negative 19 joules. Now, the fact that this is positive basically tells you that light is absorbed. So if ever this is positive, that means light is absorbed. And actually, we already knew that because we logically know that moving from low energy to high energy means that light needs to be absorbed. So just in case you see a negative sign, that means that the light's being emitted. All right, for a different problem. Okay, so now that we know energy level, let's see if we actually answer the question. Because the question is not asking for energy, they're asking for wavelength. All right, but if we know energy, we can calculate wavelength. Because we know that from this equation, E equals hc over lambda, if we know Planck's constant, if we know speed of light, which we always do, and we know energy, we can calculate wavelength. So if we solve this equation for wavelength, we get lambda is equal to hc over E. And at this point, we can just plug in. So that's equal to 6.626 times 10 to the negative 34 multiplied by the speed of light, which is 3 times 10 to the 8th, divided by E, which I just calculated as 1.55 times 10 to the negative 19 joules. Plug that in my calculator, solve. I get 1.28 times 10 to the negative 6. This is a wavelength, so don't forget your units or else you'll miss points. Meters. Because my units of wavelength is always going to be meters. And that's how you use the Rydberg equation to solve for wavelengths of emitted or absorbed light due to transition in electron energy levels.